Hi everyone, my name is Amitesh, and in this video we're going to study the following problem, which is a limiting problem. We have the function f of x over there. We want to find the limit as x goes to 1 of f of x, and we want to sketch the graph of y equals f of x. So this kind of problem, when you first see limits, they can look a little intimidating, but we're really going to dissect it and come to terms with what it's asking and really feel for the problem. So let's just dive right into it and talk about the thought process. Okay, so this is a problem that I've taught at Princeton University multiple times, teaching freshman calculus. It's a very fundamental example. So let's dive into what the thought process is for this problem. So first of all, let's write out our function, which is already given to us. And we're asked, what is the limit as x goes to 1 of f of x? So we're trying to find out limit x goes to 1 of x squared minus 2x plus 1 divided by x minus 1. Okay, so the first step we do is with limits, typically you want to figure out what is this expression approaching as x approaches 1. I mean, that's always what you want to figure out. Now, the first thing to think about is what is that expression when x is equal to 1? Okay, what does that expression look like when x is equal to 1? Because if you can plug in 1 and get something valid, that you're not dividing by 0, for example, then that is generally going to be the answer for your limit, because generally speaking, if you graph these kinds of functions, if you sort of take a ratio of two functions and the top is approaching, let's say 5, and the bottom is approaching, let's say 3, then the ratio should approach 5 over 3, right? So you can just plug in that case without doing anything. So the first step is always to plug in, and so let's just plug in here and see what we get. So if you plug in x equals 1, what happens as x, approaches 1 or x equals to 1? So the top is x squared minus 2x plus 1. So it's going to approach 1 squared minus 2 times 1 plus 1, which is just going to equal to 0. Okay, so x equals 1 is a root of the quadratic at the top. Okay, that's kind of another way of saying that. Similarly, if we look at the bottom, this is also going to approach 0. It's going to be approach 1 minus 1, which is going to equal to 0. So this is what we call a 0 over 0 limit, or a 0 over 0 indeterminate form. Okay, so typically people spell this differently. So some people spell it indeterminant, some people spell it indeterminate. I'll just interchange between the two. I'll just call it indeterminant though typically. So this is an indeterminate form. What that means is that the answer really depends on what we're actually doing with the specific numerator and denominator. I could change up the numerator and denominator and still sort of get 0 over 0, but then when I find the limit, I could get a different answer. Okay, so it kind of depends on what you're doing. So the classical example, just to kind of think about it, is if I had a limit like limit x goes to 0 of 3x over x and limit x goes to 0 of x over x, right? If you have this kind of problem, you sort of see these as 0 over 0 limits, because if you plug in 0 on top and bottom, you get 0 over 0. 3x approaches 0 as x approaches 0, and of course x approaches 0 as x approaches 0. So you would write that these are 0 over 0 indeterminate forms. However, of course, what happens here, so this is 0 over 0, and this is also 0 over 0. But of course, when x approaches 0, what is this function 3x over x? It's not equal to 3 at 0 because it's undefined. But as long as x is non-zero, you can cancel off because you're not dividing by 0. So if you cancel off the x and the x, as x approaches 0, you're just going to get limit x goes to 0 of 3, which is just 3. And here you're going to get limit x goes to 0 of 1, which is just 1. So you see that the value of the limit is really depending. If just knowing it 0 over 0 doesn't tell you what it is. It really depends on what the numerator and denominator are. So that's what we're going to have to address with that problem. So what I'm going to do is I'm going to erase this, and I'm even going to erase this here. We remember what the problem is, and we're going to try to figure out what to do there. So the typical way I look at this is that when it's 0 over 0, there is a culprit on the top and the bottom. Okay, there's a culprit that is creating a 0 on the top, and a culprit that's creating a 0 on the bottom. What does culprit mean? It means a factor. Anything times 0 is 0. Okay, so when we think about a quadratic, when you have a root at x equals 1, you can factorize the quadratic into two pieces, and the culprit is the piece that is becoming 0 when x approaches 1. The other piece is not necessarily 0. It could be anything, but that piece is not the culprit. Okay, so we need to sort of understand what is the culprit on the top and the bottom that is creating the 0 over 0, and that comes down to factoring the quadratic. Okay, so let's kind of factor the quadratic. So x squared minus 2x plus 1. So in this case, it's going to be a kind of a funny thing's going to happen. You're going to see x squared minus 2x plus 1. Well, I mean, you can use the quadratic formula if you like, or if you think about factoring quadratics in the usual way. You're trying to find a pair of numbers that sum to minus 2 and multiply to 1. Okay, so typically when you see something like this, you sort of say, okay, this is x minus 1 times x minus 1. I have a will do videos on factoring quadratics, and links will be in the description below when they're available. So please check them out if you want more details. But you can use a quadratic formula also if you like. It's x minus 1 times x minus 1. So now you sort of see that what happens with the limit, it's limit x goes to 1 of x squared minus 2x plus 1 divided by x minus 1, which is equal to limit x goes to 1 of x minus 1 times x minus 1 divided by x minus 1. Okay, so the point here is that the 0 over 0 is coming from this culprit, which is the x minus 1. Okay, so that's what you're looking for when you are having a limit as x goes to 1 and you have a polynomial on the top and the bottom and it's becoming 0 over 0. You sort of want to cancel off the x minus 1s from the top and bottom until you get something that you can sort of plug in, if possible. May not be, but in this example it will be. So what we're going to do is we're going to cancel off. We sort of say this is the culprit, this is the culprit. Of course you have the same factor twice, and that's the funny thing I was alluding to. So, you cancel one of them off. So you sort of say x minus 1 and x minus 1 cancel off because we are in the limit. Okay, so it's not correct, at 1. At 1 you have 0 over 0, which doesn't make sense. So because the limit doesn't actually say what happens at the point, but only near the point, all you have to do is just say that, okay, near the point x minus 1 is a non-zero number because x is not 1, near 1, not at 1. So you can cancel it off. And then you can sort of say that this is just going to end up being, what's it going to end up being? Near 1, as x approaches 1, it's just limit x goes to 1 of x minus 1. Okay, and now you've got something that you can plug in. You can plug in 1 into that. And it's what you'd expect. As x approaches 1, x minus 1 will approach 0, right? It's just natural there because you're not dividing by 0. All the difficult stuff with limits happens when you do some stuff like dividing by 0 maybe or something like that. Here you're not, so you can just plug in at this point and you just get 0. Okay, so you see that 0 over 0 can also just be 0 as a limit. So that's why it's called an indeterminate form, because it could be any value. You have to actually play around with it and dive in and really understand what it is. So then the next question, which was part B, is how do we actually plot the graph of this function? So this is kind of suggested to us in the limit, is we've actually understood what the function is. It looks like some weirdly complicated expression, but actually it is something very concrete. It is just x minus 1. Not quite, but almost. Okay, so if you have the function f of x, which we've just studied, which is x squared minus 2x plus 1 over x minus 1, and you have the function g of x, which we're going to write out as x minus 1, right? What we think it should be, which is x minus 1. Then yes, these are equal as long as x is not equal to 1. But when x is 1, f of x, 1 is not in the domain of f of x. Okay, so we would say here that, you can write this as the domain of f is going to equal to, in interval notation, it's minus infinity 1 union 1 infinity. Okay, so basically minus infinity 1 is all numbers between negative infinity and 1, not including 1 because you have a parenthesis. And similarly 1 infinity is all numbers greater than 1, not including 1 because you have a parenthesis, not a brackets. So a brackets would be something like, a closed brackets would be something like that, but you have a round bracket, which is a parenthesis. And the union is just you're taking them together. So you're taking all the numbers less than 1 and all the numbers greater than 1. And that's going to be the domain of f of x. But the domain of g is just going to be, equal to everything. It's all real numbers are. I've done a video on interval notation. Check it out. Links in the description down below. And if you've watched this far, please like and subscribe. Really means a lot to me. And it helps disseminate my videos to as many people as possible. And keeps you notified on new content. But let's finalize this problem. So we've got f of x and g of x. So all we have to do here is just say that the functions are equal except at 1. So they're not quite equal because their domains are different. And this is very crucial because, so I mean the reason they're equal when x is not 1, just to emphasize, is because we can cancel the x minus 1 provided x is not 1. Okay, so we can get the equation we did when we found the limits was actually an equation as long as x is not 1. So now we're just going to draw the graph of x plus 1. Right? So, or x minus 1, sorry. What's the graph of x minus 1? So it's equation of a line. What I'd like to do is just find the x-intercept and y-intercept. So when x is 0, you've got the y-intercept. So you've got minus 1. Right? That's when x is equal to 0. And the x-intercept is when g of x is 0. Okay? So g of x is 0 when x minus 1 is 0 or when x is 1. Okay, so x-intercept is a little trickier. You have to set g of x is 0. But in this case, it's a linear equation, so we can solve that. And you've got 1. And now you can just draw the graph of g of x. So you can sort of draw it. It's going to equal to this. Okay, this is the graph of g of x so far. It's x minus 1. However, the problem is, and another way of looking at it is you take the line y equals x and just translate it down by 1 because all the y values are decreasing by 1. So always good to think about things in different ways. But then of course you know that f of x does not have 1 in the domain. So what we would do is we would put this and we would, for sketching graphs, we will say a hole at the point. You can either say a hole at x equals to 1 or you can say a hole at 1 comma 0. Okay, so hole at 1 comma 0 is the most descriptive way of saying that. And that's the graph of f of x. So I just want to draw it as y equals f of x. Crazy looking function, but when you draw the graph, it's actually pretty simple. So thank you so much for watching. I hope you loved this video on a fundamental limit, something that is taught at the beginning. I've taught multiple times at Princeton University when teaching limits. Start off with this kind of example. There are many variations of them. I'll try to do other examples too. Please check out my channel. I've got a lot of videos. My goal is to create free accessible math education to everyone in the world, not just people in colleges or high schools. Everyone who has internet access should have the opportunity to learn, love, and enjoy math. And in fact, everyone without internet access should too. And ultimately, my goal is to expand things out so I can offer my educational resources to as many different people as possible, from all backgrounds, everywhere in the world. And by liking and subscribing, you really go a long way towards helping me achieve that goal. So please leave a like and subscribe. Thank you so much for watching. And I'm super excited to see you in the next video. I wish you all the best. I hope I was able to support you. You learned a lot from this. Drop a comment down below. I'd love to hear from you. I read all the comments. I'll definitely do my best to respond to as many as possible. So my name is Amitesh, signing off. See you soon.